Good day everyone! In this video, we will be explaining a
Radio
complete
waves
amplitude
control
modulation or AM transmitter
From the tunes in
and
your
receiver
car driving
circuit,
down the road to
focusing
the
on
police
how
radio
information
in the car
is
that's pulling
transmitted
you over
and
for not
recovered
signaling you
using
to turn.
analog
These
communication
waves
techniques.
are undetectable and
Amplitude
invisible to
modulation,
human
or
senses, but they
AM,
make up
is
the
one of the
foundation
fundamental
of modern
modulation
connected
methods in
technology.
electronics and
While the
communication
roots of modern
systems.
connected technologies
Even though it's
may be
considered
radio
a classic
waves,
technique,
the underlying
it is
tech
still
that makes
extremely
radio waves
important
possible
for
is a
understanding
rather
how
simple
modern wireless
concept to
systems
understand.
evolve.
Any person can make a
But
simple
first,
radio in
what
their
is
home
amplitude
for a few
modulation?
bucks, which is
In
part of
AM,
the reason this
a
foundational
high-frequency carrier
communication
signal
tech dates
is
back to
generated.
1895
A low
as a
frequency rate
demonstrable
audio signal
introduction to
carries the
understanding
information,
what radio is.
and the amplitude of the
will engage
carrier
in a
varies
simple
according to the
explanation
audio
of how you
signal.
might make one. All you need
The frequency
is a battery,
of the carrier
a coin,
remains
and an
constant,
AM radio.
while its envelope
Tune the radio
follows the
to a
modulating
static channel
signal.
and start tapping
That
that
envelope
coin on
is
the
what
two
the
terminals
receiver
of the
later
battery.
extracts.
You'll start hearing that tapping
Now,
through
our
the AM
system
radio.
is divided
By
into
doing
two main
this, you'll have
sections.
made a crude
First
radio
is the
transmitter,
transmitter, and second
capable of
is the
communicating
receiver.
in
So for
Morse
the
code or
transmitter,
random
we have the
taps
first
over just
carrier
a
signal
few inches,
generator,
though.
which
What
uses
you're
a clock
doing in this
oscillator.
process is exciting
Second,
electrons on
the modulating
transmitter side,
signal
the
with
battery,
preamplifier.
and coin, which
Third,
then is received
the
as a
AM
signal on the
modulator.
receiving side,
And
the
fourth,
AM radio,
the RF
and
power
turned back
amplifier,
into an
which
audio
uses a
output.
Class A
What you're
amplifier.
doing is completing
And
a
for the
circuit
receiver,
between the battery
we have the
terminals
RF
reached by the
amplifier,
receiver in the AM
the
radio.
demodulator,
In order to
which uses the
understand
envelope
radios
detector,
in more detail
and the
than what
audio
we've just
amplifier,
discussed,
which
we need
uses
to
a
take
non-inverting
little trip
operational
through history.
amplifier.
Back in the early
Each
days
of
of
these
radio
blocks
technology,
uses a
in
different
the
circuit
whereabouts
type,
of the early
and it's optimized for its
1900s,
specific
radio
function.
transmitter.
Let's now start with the transmitter.
For the carrier signal generator, the carrier signal in this circuit is generated using a clop oscillator, which is a modified version of the Colpitts oscillator. Just like Colpitts, the clop oscillator uses a capacitive voltage divider, a transistor for gain and feedback. However, what makes the clop oscillator different and superior is the addition of an extra series capacitor in the LC tank circuit. So why use a clop oscillator? The clop oscillator offers better frequency stability, less sensitivity to transistor and stray capacitances, more accurate frequency control, which makes it ideal for communication systems where carrier stability is critical. The clop oscillator is built around the 2N3904 NPN transistor with the following key components. First, we have the L2 that measures 10 millihenry and serves as the main tank inductor. We also have C7 and C8 that both measures 470 nanofarad and serves as feedback capacitors. Next is C9 that measures 150 nanofarad, which is the series tuning capacitors, and this what makes it a clop oscillator. Next is we also have biasing resistors, the R1 which measures 47 kilo ohms and R6 10 kilo ohms. Lastly, we have the output coupling capacitor, the C6, that measures 10 nanofarad. The oscillation frequency is primarily determined by L2 and C9, making the frequency much more stable compared to a Colpitts oscillator. Next, we have the modulating signal that has a 1 kHz audio signal with a small amplitude of 50 millivolts peak to peak. Since this level is too weak for effective modulation, we use a preamplifier, which is implemented using an LF081AC operational amplifier. This is a voltage amplifier circuit configured to increase signal amplitude without altering waveform shape. Key components include R8 that measures 100 kilo ohms and serves as the input resistor. We also have the feedback and gain control, the R7 and R9 that both measures 15 kilo ohms. We also have the positive and negative 12 volts dual supply. This ensures the audio signal is strong enough to control the modulator stage. We also have the modulator stage, which is built using another 2N3904 transistor operating in the active region. The important components are the L1 or the RF choke, which measures 100 microhenry, and also we have the R2 that measures 68 kiloohms and the R4 22 kiloohms, which are the bias network. Next is the R5, which measures 100 kiloohms and serves as the emitter resistor. We also have the RF coupling, the C1, that measures 47 nanofarad, and the two bypass capacitors, which is the C3 and C4 that both measures 10 microfarad. This stage acts as a nonlinear mixing circuit where the carrier is applied to the collector. The audio signal modulates the base bias and the output becomes an amplitude modulated signal. Next, the RF amplifier, where the modulated signal is then passed through a Class A RF amplifier using a 2N3904 transistor. Key components include R10 and R13 that both measure 68 kiloohms and serves as the collector bias. Next is the R11 that measures 22 kiloohms, which serves as the base bias. Next is the emitter resistor, the R12, which measures 100 kiloohms. Lastly, we have the two coupling capacitors, the C11 and C12, that both measures 10 microfarad. As we've said earlier, this is a Class A amplifier, which means the transistor conducts for the entire signal cycle. It provides excellent linearity, and it preserves the envelope of the AM signal. Although Class A is inefficient, it is perfect for low-power communication demonstrations.
Moving on to the receiver section, so for the RF amplifier, we have the common emitter amplifier. As you can see, at the receiver, the first block is an RF amplifier, which boosts the incoming AM signal. This is a common emitter amplifier, chosen because it provides high voltage gain and good signal sensitivity. This stage ensures that weak received signals can still be properly demodulated.
For the next one is demodulator, envelope detector, which is diode detector. The demodulator is a class envelope detector, which is the simplest and the most common AM demodulation circuit. It consists of 1N4149 diode rectifier, C13 1 microfarad smoothing capacitor, and last R14 750 ohms potentiometer load resistor. This is a nonlinear detection circuit. The diode removes the negative half of the waveform, while the RC network extracts the envelope, which corresponds to the original audio signal. Correct capacitor and resistor values are crucial. Too large, which is distorted audio. Too small, which is noisy output. And last, audio amplifier, a non-inverting op-amp. After demodulation, the recovered audio signal is very weak. To solve this, we use a non-inverting audio amplifier based on a 741 operational amplifier. Key components: R15, 500 ohms, which is input resistor. R16, 100 kiloohms potentiometer, which is a feedback resistor gain control. And last, positive-negative 12 volt supply. And for the next one, this configuration provides a high input impedance. And next, adjust the gain. And last, no phase inversion. The output is a clear, amplified audio signal, suitable for listening or further processing.
Here is the video for the modulator. First, as you can see, there is the carrier signal, the modulating signal, the modulated signal, and the amplified signal, which is ready for transmission. Meanwhile, here is the demodulated signal. So as you can see, there is the demodulated signal, the amplified demodulated signal, and the received signal, which is the modulated signal. To conclude, we can say that the clap oscillator provides a stable carrier, the preamplifier boosts the audio signal, the modulator creates the AM waveform, the Class A amplifier strengthens the signal for transmission, The receiver amplifies, demodulates, and recovers the audio. This project demonstrates a complete AM communication system, highlighting different circuit types working together to transmit and receive information. Thank you for listening, and we hope this presentation helped you better understand how real AM transmitters and receivers are built and analyzed.